It's definitely not going to be your typical physics lecture. So get ready for some aha moments as we kind of explore how the universe works at its tiniest levels.
Yeah, for sure.
We're talking about particles behaving like waves,
Mm-hmm.
objects existing in multiple states at once, all kinds of crazy stuff.
It's pretty mind-bending stuff, but it's also super captivating once you kind of wrap your head around it.
Yeah, definitely. So to start off, I think it's important to remember that quantum mechanics really governs the universe at its most fundamental level,
Yeah,
right?
yeah, you got it.
Like we're talking about the realm of atoms and subatomic particles, and that's where everyday intuition just kind of breaks down.
Totally. Yeah, it's a completely different world down there.
So let's dive into one of the core concepts that you sent over, which is wave-particle duality. So instead of thinking of like light as just a wave or an electron as just a particle, quantum mechanics tells us that they can behave as both.
Right. And and it's not even that they're like switching back and forth, you know?
Oh, really?
What's wild is that they exhibit properties of both waves and particles like at the same time.
Oh, wow.
Yeah. And I think one of the best ways to really illustrate this is with the electron diffraction experiment.
Okay.
So imagine you're firing a beam of electrons, through a narrow slit.
Mm-hmm.
Now, if electrons were just particles, you would think, okay, they're just going to pass straight through in a straight line, right?
Right. Yeah, makes sense.
But what happens is they create this pattern on a screen behind the slit, just like waves interfering with each other.
So even though they're individual particles, they're still creating this wave-like pattern.
Exactly. It's like each electron is somehow interfering with itself.
Whoa, that's
Oh.
trippy. So does that mean that everything is both a wave and a particle then?
That's a great question. It's mostly something we see at the, atomic and subatomic level.
Okay.
So in our everyday macroscopic world, you're not really going to see, a baseball behaving like a wave.
Right.
But this duality is still like fundamental to how everything works.
Oh, wow. Okay. I'm starting to see how quantum mechanics really kind of challenges our normal ways of thinking about things.
Yeah, definitely.
All right. So let's move on to another key concept that you sent over, which is quantization.
Okay.
So I kind of think of this like a musical instrument producing specific notes, right? Because the sound waves are quantized.
Mm-hmm.
Like you can't play half a note on a piano.
Yeah, that's a really good analogy.
It's like everything is in these specific little packets.
Exactly. And in the quantum world, energy momentum and other properties, they're not continuous like they are in classical physics. They
Right.
exist in these specific discrete packets, or quanta as they're called. And so it's kind of like the universe has this set of building blocks that it uses to construct reality. And mathematically, this quantization is often the result of the wave nature of particles and, the boundary conditions that they experience.
So is a quantum like the smallest possible unit of energy then?
Yeah, you can think of it that way. Like a quantum is the smallest amount of energy that can be exchanged in a particular interaction.
Yeah.
It's not that energy itself is fundamentally chunky, but rather that interactions happen in these discrete steps. And this has, huge implications for understanding how atoms behave, for example.
Okay, that makes sense. So now let's talk about something that always kind of makes me think, which is Heisenberg's uncertainty principle.
Yeah.
It feels almost philosophical, like there's this limit to what we can actually know about the universe.
Right. And the uncertainty principle, it basically tells us that we can't know both the position and momentum of a particle with perfect accuracy at the same time.
So like even if we had infinitely precise instruments, there's still this fundamental blurriness to reality at the quantum level.
Yeah, exactly.
Wow, okay.
And it's not a matter of our measuring tools being, bad. It's a fundamental principle.
That's crazy.
Yeah, and so the more precisely we know a particle's position, the less we can know about its momentum, and vice versa.
So it's almost like the act of measuring one property affects the other.
Yeah, and that's actually a really deep question that's puzzled physicists and philosophers for decades.
Mm-hmm.
Some interpretations of quantum mechanics suggest that the observer actually plays a role in collapsing the wave function of a system, essentially forcing it to choose a specific state.
Oh, wow. So until we measure something, it could be in multiple states at once. Is that kind of what superposition is all about?
Exactly. Yeah.
Yeah.
Superposition is this idea that a quantum system can exist in this combination of multiple states simultaneously until it's measured.
So it's not just that we don't know which state it's in, it's actually in all of those states at the same time.
Yeah, kind of. It's a very strange concept to think about. I like to think of it like a coin spinning in the air, right?
Yeah.
It's neither heads nor tails until it lands. And in the
Mhm.
same way, a quantum system can exist in a superposition of states until an observation or a measurement kind of forces it to choose one.
Wow, that's really interesting. And that's actually one of the things that makes quantum computing so powerful, right?
Yeah, exactly. Qubits, which are the building blocks of quantum computers, can leverage superposition to explore multiple possibilities simultaneously.
So it's like having massive parallel processing power at your fingertips.
Yeah, you got it.
Wow. It sounds like we're only just scratching the surface of the weirdness of the quantum world.
Oh, yeah, definitely. There's a lot more to come.
So what's next? What else do we have to dive into?
Well, next we're going to get into something that even Einstein found spooky, and that is entanglement.
Oh, yeah.
So imagine two particles that are linked in a way that their fates are intertwined no matter how far apart they are.
That sounds insane. I can't wait to hear more about that.
Yeah.
All right, so we left off talking about entanglement, and it sounds like something straight out of science fiction, you know?
It's definitely one of the most mind-boggling concepts in quantum mechanics. So basically you have these two entangled particles, and measuring the state of one particle instantly determines the state of the other no matter how far apart they are.
But how is that even possible?
Oh,
Doesn't that violate the idea that nothing can travel faster than the speed of light?
that's the thing. It's like they're connected by this invisible thread that transcends space and time.
Wow.
Yeah, it seems to completely defy our classical understanding of locality.
Yeah, for sure.
It's as if the two particles are actually part of a single unified system, even when they're separated by, huge distances.
It's almost like they're communicating with each other instantly.
Yeah, and that's exactly what Einstein struggled with. He called it spooky action at a distance.
Yeah, I've heard that.
But numerous experiments have actually confirmed that this is a very real phenomenon.
That's incredible. So what are the implications of this? Like, where could we actually use this?
Well, entanglement has the potential to revolutionize a lot of different fields like communication and cryptography.
Yeah.
So imagine a world where information could be transmitted instantly and securely across vast distances just using entangled particles.
Yeah, that would be game-changing.
Exactly. That's the promise of quantum communication.
Wow. Okay, so let's shift gears a bit. We've been talking about particles behaving like waves, energy being quantized, and all this uncertainty surrounding their properties. So how do we actually make sense of all of this in a mathematical way?
Right. So that's where the concept of the wave function comes in.
Okay.
And in quantum mechanics, we don't deal with certainties, but rather with probabilities. So the wave function is represented by the Greek letter Ci, and it's basically this mathematical function that describes the state of a quantum system.
Yeah.
And it contains information about all of its possible states.
So instead of saying, like, the electron is located here, we're saying there's a certain probability of finding it in various locations.
Exactly.
Yeah.
The wave function doesn't tell us exactly where a particle is, but rather where it's most likely to be found.
So it's like a map of possibilities,
Yeah, you could think of it that way.
showing us the likelihood of different outcomes.
Right. And the square of the wave function actually gives us the probability density of finding a particle at a specific location.
Okay, that makes sense.
Yeah.
It's fascinating how probability is just woven into the fabric of reality at the quantum level.
Yeah, for sure. Now, we've been talking a lot about quantum mechanics as a separate theory,
Yeah.
but it doesn't exist in isolation. There's also quantum field theory, which combines quantum mechanics with special relativity.
Whoa, so we're merging quantum mechanics with relativity. That sounds intense.
Yeah, it is, but it's incredibly powerful. And so in quantum field theory, particles are actually seen as excitations of these underlying fields that permeate all of space-time.
So instead of thinking of particles as these tiny, solid objects, we're thinking of them as disturbances in these quantum fields.
Exactly. It's like if you imagine the universe as this vast ocean of energy,
Okay.
and particles are like ripples or waves on the surface of that ocean.
I like that analogy.
Uh-huh.
So what kind of fields are we talking about here?
Well, there are fields for each of the fundamental forces of nature.
Okay.
So, for example, you have the electromagnetic force, which is mediated by the photon field. And then you have the strong force, which holds atomic nuclei together, and that's mediated by the gluon field and so on.
Okay, so there's a field for every force.
Yeah, and quantum field theory provides this really unified framework for understanding particles and forces.
So it sounds like quantum field theory offers a really elegant way to describe the universe. Does it explain everything, though? Like, what about gravity?
Yeah, that's the million-dollar question.
Yeah.
Quantum field theory has been super successful in describing the electromagnetic weak and strong forces, but incorporating gravity into this framework has proven to be a really big challenge. Yeah. Quantum field theory and general relativity, which is Einstein's theory of gravity, they just haven't been fully reconciled yet.
So we have this beautiful theory that describes the quantum world, and we have general relativity that describes gravity, but we haven't figured out how to make them work together.
Yeah, that's the problem. Unifying quantum mechanics and general relativity is one of the biggest unsolved problems in physics.
So it makes you wonder if there's some even deeper theory out there that encompasses both of them.
Right. And there are some promising candidates, like string theory.
Okay, I've heard of that.
Yeah.
Right.
This theory suggests that the fundamental building blocks of the universe aren't these point-like particles, but tiny vibrating strings.
Okay.
And the different vibrations of these strings would give rise to the different particles and forces that we observe.
So instead of little billiard balls, we have tiny vibrating strings. It's like the universe is a giant cosmic orchestra.
Exactly. Yeah. It's a really fascinating idea. And one of the most appealing aspects of string theory is that it naturally incorporates gravity.
Oh, what?
So it has the potential to be this unified theory of everything providing a single framework for understanding all the fundamental forces.
That's pretty incredible. But you mentioned that string theory is just a candidate.
Right.
Are there other approaches to unifying quantum mechanics and gravity?
Yeah, there are other approaches like loop quantum gravity, which takes a different approach to quantizing gravity. So instead of thinking of space-time as this smooth, continuous fabric loop, quantum gravity suggests that it's actually made up of tiny, discrete loops.
Okay.
And these loops would have a minimum size, which means that space-time itself is quantized at the Planck scale.
So instead of a smooth sheet, it's more like a finely woven tapestry.
Exactly.
Wow. So what are the implications of that?
Well, one interesting consequence is that loop quantum gravity avoids the singularities that plague general relativity.
Okay.
So these are points in space-time where density and curvature become infinite, like at the center of a black hole.
Yeah.
But in loop quantum gravity, space-time has this granular structure, and there's this minimum size below which it just can't be squeezed.
It sounds like there's still a lot we don't know about how gravity fits into the quantum picture.
Yeah, definitely.
Yeah.
There's so much more to explore.
All right, well, I'm ready to continue this journey. What else is there to discover in this quantum world? Welcome back to our deep dive. I feel like we've journeyed through some pretty mind-bending concepts.
Yeah, it's been a wild ride, for sure.
From, wave-particle duality to, even searching for a unified theory of everything.
I know. It's a lot to take in.
It really is. It's incredible how much our understanding of the universe has changed thanks to all this.
Yeah, and we've only just scratched the surface when it comes to, the potential applications of these principles,
Speaking of applications, one area that I'm particularly fascinated by is quantum computing.
Oh, yeah.
Especially the idea of qubits you mentioned, that they can be in a superposition of states.
Right.
Like both 0 and 1 at the same time. So how does that actually work and what makes it so powerful?
So imagine a regular computer bit. It can either be a 0 or a 1. Like a light switch that's either on or off.
Right.
But a qubit is more like a dimmer switch.
Okay.
It can be set to various levels of brightness.
Oh, I see.
So it can be in a superposition of both states simultaneously.
So it's like having this massive parallel processing power.
Exactly.
What kind of problems are best suited for that then?
Well, quantum computers are really good at tasks that involve searching through huge amounts of data or simulating complex systems. For example, they could revolutionize drug discovery.
How so?
Well, they could simulate the interactions of molecules at the atomic level.
Oh, wow.
And that could lead to new medicines and new materials.
Yeah, that would be huge.
Yeah, and they could also break the encryption algorithms that we use to protect online transactions.
Oh, wow. So it's kind of like a double-edged sword then.
Yeah, definitely. It poses both a challenge and an opportunity for cybersecurity.
So it sounds like quantum computing could have a really profound impact on every aspect of our world.
Yeah. For sure.
But I imagine there are still some technical hurdles to overcome.
Oh, yeah, absolutely.
Like what kind of things?
Well, one of the biggest challenges is maintaining the coherence of qubits. They're super fragile and easily disturbed by their environment.
Right.
Which can lead to errors.
Yeah, that makes sense.
And then scaling up quantum computers to handle more complex problems, that's another major hurdle.
So it's still pretty early days, but the future of quantum computing is looking pretty bright.
Oh, yeah, definitely. It's one of the most exciting areas of research right now.
Before we wrap up, I want to circle back to the philosophical implications of all this.
Okay.
This whole journey through the quantum world has really challenged my assumptions about reality.
Yeah, it's definitely a field that raises a lot of profound questions about the nature of reality, the role of the observer, the limits of knowledge.
Like the idea that a particle can exist in multiple states until it's measured.
Right.
It suggests that observation itself somehow influences reality.
Yeah, that's one way to interpret it. The Copenhagen interpretation, which is one of the most widely accepted interpretations of quantum mechanics, it suggests that the act of measurement actually collapses the wave function of a system, forcing it to choose a definite state.
So does that mean that consciousness plays a role there?
Well, that's a question that sparked a lot of debate.
Mm.
Some physicists believe that consciousness is essential for this collapse, while others think it's just a physical process that has nothing to do with consciousness.
And then we have entanglement.
Yeah.
Where these two particles are linked across vast distances.
Yeah.
That suggests like a level of interconnectedness that's just hard to even grasp.
Right.
Does this tell us anything about the universe as a whole?
Well, it definitely challenges our classical intuitions about space and time.
Right.
It suggests that there are connections between things that go beyond our understanding of locality.
So crazy.
And some physicists even think that entanglement could play a role in, like, the origins of the universe itself.
It's incredible to think that these, like, strange and counterintuitive principles are not just theoretical.
Yeah.
They're actually how the universe works.
It really is mind-blowing.
And the more we learn about the quantum world, the more we realize how much more there is to learn.
Absolutely.
Well, on that note, I think it's time to wrap up our deep dive. It's been an amazing journey.
It really has.
Full of just mind-blowing insights and thought-provoking discussions.
I agree. It's been a pleasure exploring these concepts with you.
And to all of our listeners, thank you for joining us on this adventure into the quantum realm.
Yeah, thanks for listening, everyone.
We hope you've enjoyed it as much as we have.
Remember, the quantum world is all around us, even if we can't see it directly. It's shaping everything from the atoms in our bodies to the stars in the sky.
So keep questioning, keep exploring, and keep your minds open to the wonders of the quantum universe.
Yeah, who knows what amazing discoveries await us in the future.
Definitely a lot more to come, I'm sure.